Welcome to our next video on condensed matter theory. What I want to discuss in this lecture is the derivation of Ohm's law from the Drude model. And Ohm's law basically relates the current through a rod of metal to the voltage that we put over that rod of metal. If we have some rod of a metallic substance with length L and area A, and then we connect it and put a voltage over this, then a current will flow, a current I, and we know that the voltage is equal to the current times the resistance. We can actually express the resistance in terms of a material constant and the length of the rod divided by the area. So the longer we make the rod, the bigger the resistance, the thinner the rod we make the rod, the bigger the resistance. Ohm's law has been reformulated by Kirchhoff. And it is the notation of Kirchhoff that we will use. And Kirchhoff talked about the current density, so that we do not have to consider the area anymore. And the current density is related to the conductivity times the electrical field. And the voltage is related to the electrical field times the distance, such that also here the length drops out of the equation. So E is our electrical field. And J is the current density. Now, when we have a metal with an electron density N, we can actually express the current density in terms of the electron density. And it's the electron density times the charge of the electrons, which is minus E, such that E is a positive number, times the average velocity of our electrons. The electrons can move in all directions, but on average, if they have something that is left, then you generate a current. So this is the electron density. And this is the average velocity. Now let's see how we can calculate derive what sigma should be from using Drude's model. And we assume that we have an homogeneous electrical field, which we have in this setup. We then can calculate the velocity, and now the velocity depends on time. And at some point in time, the electron scatters. We can take that as our time zero. After a scattering event, we have a velocity v0, which is orientated in some direction and has a length or value such that p squared over 2m is the kinetic energy is 3/2 k-Boltzmann-T. And then this electron starts to accelerate with the electrical charge times the field times time over m. So the acceleration is EE divided by m, such that the velocity is EET divided by m. And t, here is the time after a collision. And v0 is the velocity after a collision. We now can calculate what the average velocity is, averaging over all electrons. And that is the average velocity that we have just after a collision minus the average over all electrons, EET divided by m. Well, the average velocity just after a collision is equal to 0. And we now have to look what the average is for EE of the time after a collision divided by m. So then we have to know what the average time is between two collisions, and that is t, tau. So we can replace t by tau. Let's have a look at this a bit more carefully. So this is an integral, because I can of course have an electron that immediately scatters after a previous scattering event, or takes extremely long after a scattering event. So I have to integrate from 0 to infinite. Then the velocity that I have at that point in time. Then the probability to scatter at time t, which is 1 over tau dt. And then of course I have to multiply with the probability that in a time from 0 to t you haven't scattered, which is e to the minus t over tau. And if you evaluate that integral, you indeed get what we said before, the average time between two scattering events. We can now put in the average velocity in our equation here, and we shouldn't have a 0 here, such that our current is given by minus NE times minus EE is a plus, n E square tau over m times the electrical field. And indeed we find that the current density is linear proportional to the electrical field in our system, such that we have Ohm's law. And we also find that we can define a conductivity as n E square tau over m. So it depends on the electron density that we have in our system, the electrical charge, a scattering length divided by the mass of the electrons. This is of course one of the first successes of Drude's model, that he can explain why Ohm's law and shows you that conductance is linear, or resistance is linear, coupling volt and current, or current density and electrical fields. Well, in the next video we'll have a look what happens when we put on an additional magnetic field, and then explain the Hall effect and which properties you can measure with the Hall effect. Thank you very much for your attention. We'll see each other in the next video. Stay healthy.